Okay, we left off with this question. We had just finished solving this first part. So we've completed this one. The next one, we have a reaction with this alkene and HCl. Now again, it doesn't ask us to draw the mechanism. However, I think it's fun to give that a shot. So we have HCl. Remember, the rich are going to get richer. And this carbon has one hydrogen on it, where this one has 0. So that's the one that's going to take the hydrogen after my proton transfer. And so my carbocation is going to look like this, like that. I'm going to have a tertiary carbocation, which is not going to undergo rearrangement. When my nucleophile, the chloride, comes in and attacks, there's no chiral center being formed. And so there's only one, there's only one isomer, there's no stereoisomer, there's only one compound, and it's achiral, I should say. More correct. And so this is the only product that we get in this one. Again, this is an achiral compound. Achiral, there we go. Let's move that out of the way and we'll give the next one a shot. So the next one, we're adding HI across the double bond. So let's see, same thing, Markovnikov addition. The rich are getting richer. So we're going to have the hydrogen being added to this carbon, and we're going to end up with, we're going to end up with this carbocation here, which is tertiary. It's not going to undergo rearrangement. However, we are going to produce a chiral center after the nucleophile attacks. I should have put this in brackets since it's an intermediate. Anyhow, so now our iodide is going to come in. We get our nucleophilic attack like this, and we end up with two stereoisomers. One where we have, so something like this, with the iodine coming out in front, and then we have another one, where we have the iodine in the back and the methyl group out in front. And the relationship between these two compounds is that they are enantiomers. Enantiomers. All right, non-superimposable mirror images or enantiomers. Next, we're going to take a look at question 8.6, which asks us to identify the reagents that you would use. If we look at A, could I ask you in A, is the hydrohalogenation occurring via a Markovnikov or an anti-Markovnikov addition? In A, is this Markovnikov or anti-Markovnikov addition of HBr across the double bond? Exactly. This is Markovnikov, isn't it? This is Markovnikov because the rich are getting richer. This carbon has 2 hydrogens on it, and now it's got 3 hydrogens on it. So the only reagent that we would need here would be HBr, nothing else. Whereas in the one below it, this proceeds via anti-Markovnikov addition, and so we would need HBr and peroxides in order to get that reaction to work. There we go. So that covers hydrohalogenation. Now we're going to move on to the next section, section 8.6, which deals with acid-catalyzed hydration. So you can imagine if you say you're hydrating something, you're adding water to it. So we can think of water as being H2O. We could draw the Lewis structure. We could write the condensed formula. They mean the same thing, but we're going to think about it as adding a hydrogen to one carbon and the hydroxyl, an OH, to the other carbon. And it is also going to proceed via Markovnikov regioselectivity. The rich are going to get richer. So if we treat this alkene with H3O plus hydronium, which is just acid dissolved in water, we're going to end up with this tertiary alcohol. Why? Because the rich are going to get richer. We're going to proceed through this tertiary carbocation, which is then going to undergo nucleophilic attack to produce the tertiary alcohol. Now, if you're wondering about what is the acid catalyst, well, sulfuric acid is often used as the acid catalyst, and that's what we mean by these square brackets. This square bracket represents that the H2SO4 is a catalyst. But again, and I've gone over this with you many times in class, if you take sulfuric acid and you put it in water, what's actually predominating is going to be hydronium and the conjugate base of sulfuric acid. Why? Because the pK of sulfuric acid is -9 and the pK of hydronium is -1.7. The equilibrium is going to lie to the side of the weaker acid. That's why we don't write H2SO4 over water. Okay, you can write that. That's reasonable. But we know that in the mixture of acid and water, what's going to be doing the protonating or the proton transfer is hydronium. What's going to do the nucleophilic attack will be the conjugate base of hydronium, which is water. So that's why we write this. Or sometimes we'll put sulfuric acid in brackets to say it's just a catalyst to produce hydronium. So if acid-catalyzed hydration proceeds through a carbocation intermediate, which it does, then it stands to reason that the more substituted the carbocation that's produced as an intermediate is going to produce a reaction that occurs at a faster rate, right? If we were to use these three different alkenes, the first one would produce a primary carbocation as an intermediate. We know that's very unstable. The second one would produce a secondary carbocation, better. And this one would produce a tertiary carbocation, which is the most stable of all. And you can see that the reaction rate is billions of times faster than the reaction rate with a primary carbocation, which essentially isn't going to happen because a primary carbocation is so unstable. And so the rates of these reactions that we see is consistent with the idea of the mechanism proceeding through a carbocation intermediate. They go together. It makes complete sense. There's a rationale for it. Well, let's take a look at that mechanism in more detail. Remember, the first step is familiar to us, the proton transfer, the same step that we saw with hydrohalogenation, except now our acid is hydronium. So in our proton transfer step, the pi bond is going to grab on to that hydrogen, and we end up with a carbocation. Again, this proceeds via Markovnikov addition. The rich get richer. We produce that tertiary carbocation, then water can come in as a nucleophile. But when water comes in as a nucleophile, we do not make an uncharged species, do we? What we end up with is an oxonium ion. Okay, we have an oxonium ion. That's not neutral. And thus, water must come in and function as a base to deprotonate the oxonium ion to produce the alcohol. But what happens when the water grabs that proton, okay, when the water grabs this proton, you also end up producing H3O plus. That's your acid regenerated. It's a catalyst, right? The strong acid is a catalyst, so you keep making H3O plus over and over and over in the reaction. Well, let's take a look at elimination and compare it to hydration. We talked about this reaction in chapter 7, where we could take an alcohol and treat it with some concentrated sulfuric acid and heat it up. So sometimes we put a little delta symbol there, and that would remove water. Okay, and we would end up with the Zaitsev alkene. Well, think about it. What's happening now in chapter 8 is that we're treating the molecule with a catalytic amount of sulfuric acid, so just a small amount in water. So this whole thing is based off of Le Chatelier's principle as to whether we get elimination or addition. Right? If we add a ton of water, think about this very carefully. If you have a pile of water, if you're in very dilute conditions, it means that this concentration is very high, which is going to produce or push the reaction towards the alcohol. Whereas if you're doing it in concentrated sulfuric acid, that means the amount of water is super duper low. So that's going to push the reaction towards the alkene. And so not only is it based off of Gibbs free energy, but it's also a representation of Le Chatelier's principle. And so you need to know both of these reactions. If we want to make the alcohol from the alkene, we use dilute sulfuric acid. So this is when we just write H3O plus. Whereas if you want to make the alkene, the Zaitsev alkene, from the alcohol. You treat it with concentrated sulfuric acid and you heat it up. Okay, and that's going to drive water out of the molecule and produce an alkene. All right, so this would be chapter 8, and the one on the bottom would be chapter 7. Addition versus elimination. Make sure you're fully aware of these two sets of conditions. Now, what about stereochemistry? The hydration reaction proceeds through a carbocation intermediate. And we know that if we produce a carbocation, like this one here, when we produce that carbocation, we know that this carbocation is sp2 hybridized. It is trigonal planar. Therefore, when the water comes in, it can attack from the front face of the molecule, or it can attack from the back face of the molecule. In this case, we would end up with a racemic mixture, a 50-50 mixture of a pair of enantiomers, an equal amount of R and S. So we have to take stereochemistry into consideration as well. Now, if you're wondering, well, hold on, Mr. Dion, you've talked about stereochemistry and the carbocation, you talked about carbocation stability and the rate of reaction. What about rearrangements? Can't they occur? Isn't that a thing too? Rearrangements is totally a thing, and it totally can occur, but we're going to address that in the next section. Okay, we'll address rearrangements in section 8.7. So let's look at another practice problem. And I like drawing mechanisms. And this reaction says draw a mechanism. And this one is actually going to involve a rearrangement. So not only will the rearrangements be addressed in the next section, but they're also addressed in this problem. So take a peek. We have our hydronium molecule. I'm going to draw the entire Lewis structure, which you have to do to draw a proper mechanism. You cannot draw proper curved arrows without drawing the Lewis structure. The rich are going to get richer. This carbon has 2 hydrogens that I'm labeling in red. This one has 1. The one with the 2 hydrogens is going to take on the extra hydrogen. So I like to drag my pi bond through the carbon that's going to take the hydrogen, and we're going to end up making a carbocation. So let's draw that carbocation, which is going to look like this. And of course, I've produced water here as well. This is a secondary carbocation. Can this carbocation undergo a carbocation rearrangement? Well, yeah, it can, because if you were to draw water as your nucleophile, and water is the nucleophile, if you were to draw it to attack here, that would not put it in the right position, right? You can see from the product that the water is going to have to attack this carbon. We know that there is a hydrogen on here, and we can get a hydride shift. So we can get this hydride shifting over to give us a tertiary carbocation. That's what we need. Now our water molecule can act as a nucleophile. So our water acts as a nucleophile. You can draw it like this. You can draw the whole Lewis structure of the water. This, which is the way they do it in the solutions manual every time. And you draw the nucleophilic attack. There's no stereocenters in the molecule, so no need to worry about that. And we produce an oxonium. So we produce an oxonium like this, but then in order to get to our product, we have to do a proton transfer. So now water is going to come in as a base, and it's going to take that proton to give us the final product, plus we end up regenerating H3O plus, and that's a good thing since that's our acid catalyst. The catalyst has to get reformed over and over and over. Now, you might be wondering, okay, Mr. Dion, I see that you can get a carbocation rearrangement. That's great. Is there any way that we can avoid a carbocation rearrangement? Is there any way we could prevent this from happening? Like, let's say we wanted to take this molecule. So this is just the substrate. I'm just redrawing it down here. Is there a way that we could just do this? Like, just do the Markovnikov addition and avoid the carbocation rearrangement? Let me draw this a little prettier. Is there a way to do that? And the answer is yes, there is a way to avoid carbocation rearrangements. And the way that we do that is by employing special conditions that we call oxymercuration-demercuration. Pay close attention. Up until now, everything that we've gone over, I've expected you to know the mechanisms. So I want you to know the mechanism of hydration and hydrohalogenation. I guess that anti-Markovnikov addition, you don't have to know the mechanism of that. That's covered in chapter 10. So let's review. We've covered hydrohalogenation. You need to know the mechanism of this reaction. Then we looked at anti-Markovnikov addition across a double bond. That we're going to cover in chapter 10. Chapter 10. The next thing that we've covered is hydration. I want you to know the mechanism of hydration. And now we're getting to section 8.7. We're going to cover these conditions. You can see that it involves mercury, oxymercuration, and then the second step is what we call demercuration. You do not need to know the mechanism of this reaction. However, little asterisk on that. Just because I tell you you don't need to know it, I'm never going to ask you the mechanism. Think about any subject you've ever taken in school that you enjoyed. Why did you enjoy that subject? It's because you understood it. And the mechanism is presented partially in our textbook. And if you understand it just a little bit, and I'll cover it a tiny bit with you, it's going to make understanding, or remembering oxymercuration, demercuration that much easier. All right. So again, for section 8.7, you don't need to know the mechanism, but we do talk about it a little tiny bit to provide you with a little bit of rationale as to why it happens. It's a Markovnikov addition of water that avoids carbocation rearrangement. So let's go all the way back from whence we came, which is way back here. Here we go. Oops. And yeah, here we are. Section 8.7. Oxymercuration, demercuration. So this is a set of steps. The first step is to treat a molecule with mercuric sulfate, or sorry, mercury 2 acetate. So the first step is mercury 2 acetate and water. And the second step is sodium borohydride, so NaBH4. So HgOAC2, that's mercury. The book usually calls it mercuric acetate. So I'll scribble that in here. And then NaBH4 is sodium borohydride. All right, that's enough about that. Here we go. Follow along with me. It says, Markovnikov hydration, catalytic amount of sulfuric acid and water, has limited application because if you can have a carbocation rearrangement, it's going to happen. Then you usually get a mixture of products. Organic chemists love to avoid mixtures because when you get a mixture, then you've got more than one thing and you've got to find a way to separate them from each other, which can be very complex. And so we have an alternative to do a Markovnikov addition of a hydrogen and a hydroxyl, Markovnikov addition of water, and we avoid carbocation rearrangements. The first step is what we call oxymercuration. That's using the mercuric acetate and water. And then the second step is the demercuration. That's where we use the sodium borohydride. So step 1 is using mercury 2 acetate in water. And the second step is using sodium borohydride. 2 separate steps. Step 1 and step 2. Now, a little bit more about this mercuric acetate, HgOAC2. The mercuric acetate, the mercuric cation is a Lewis acid instead of a proton. So what happens is it can undergo the loss of an acetate group, and you see an acetate group, so OAC minus would be the same thing as O. This is an acetyl group. If you've ever studied acetyl coenzyme A, So this is an acetyl group here. So you end up losing the acetate group. So this is called an acetate ion. And you form this mercuric cation. Now here's where it gets interesting. The double bond of your alkene can react with the mercuric cation. If we just do a straight ahead hydration or hydrohalogenation, we produce a carbocation, whereas when the pi bond attacks the mercuric cation, we form what's called a mercurinium ion. So check this out. You have this mercurinium ion here. You can see that the side that's less sterically hindered is the one that took on the mercury, but there's a pair of electrons on the mercury, which can dump electron density into the carbocation. And so the mercurinium ion is kind of like a hybrid of this carbocation, but also this structure here where you have a three-membered ring and the positive charge is on the mercury instead of on a carbon. All right, in the mercurinium ion, what's so cool about it is that it's not going to rearrange. Why? Because it stabilizes the carbocation. It's not going to do any kind of rearrangement whatsoever, that mercurinium ion. Now here's where it is also interesting. Why would the nucleophile end up on the more substituted carbon? Or why would it attack the more substituted carbon? It's because if you think about these two contributors to the mercurinium ion, the positive charge is going to be on the more substituted carbon. Therefore, the nucleophile is going to attack that more substituted position. Now, our book goes into a little bit more detail about it, but that will suffice for now. And once you formed this intermediate, it undergoes the demercuration reaction with sodium borohydride. Now that undergoes, or that mechanism occurs via free radicals. So a free radical mechanism, and we don't cover radicals until chapter 10. And so you don't need to know anything about the mechanism of demercuration, okay? And again, I'm not going to ask you to draw this mechanism, and I'm not going to ask you to draw any of these curved arrows here. However, I want you to understand that the mercurinium ion is not going to undergo any rearrangements, and the nucleophile is going to attack the more substituted carbon. So essentially, you get Markovnikov addition that occurred with no possible rearrangement. Check it out. If you were to try this hydration reaction, so treating this alkene, so this is what? 3-methyl-1-butene with aqueous acid. You produce this secondary carbocation, right? After the proton transfer, and that can undergo a hydride shift to produce this carbocation that I'll draw over here. The carbocation in red is going to produce this product, and the carbocation in blue is going to produce this product. However, if it proceeds through oxymercuration-demercuration, you end up forming a mercurinium ion. So I'll try to draw it the best I can. And I'm going to draw the three-membered ring like this, where you have the positive charge on the mercury. And then the nucleophile, which is the water, your water comes in and it's going to attack the more substituted carbon like this. Okay, and so you're going to end up with the oxygen-hydrogen bond on that carbon, and after demercuration, you get the product that occurred via no rearrangement. Maybe I should use a blue circle to stay consistent with the conditions above. Give me a thumbs up on, you just follow me. These are the reaction conditions that we use if we want to add water across a double bond and we don't want any carbocation rearrangements. Now, just remember, we haven't looked at any reactions yet that I can think of that are two steps. One step, first step, mercuric acetate and water. Second step, sodium borohydride. If you were to just write those as mercuric acetate, water, and sodium borohydride, like this. If you were to write that on a quiz, that's wrong. It's not correct. You have to write them as individual steps. If you were to combine all those reagents together, it wouldn't work. All right, so a two-step reaction. You need to be aware of when a reaction in organic chemistry is a one-step reaction versus a two-step reaction. The one-step, two-step, right? Anyhow, question 8.16 says predict the product for each reaction and predict the products if an acid-catalyzed hydration had been performed rather than an oxymercuration-demercuration. Let's take a look at the first one. It's going to be the Markovnikov addition of water across this double bond. Why? Because we're employing oxymercuration-demercuration conditions. And so the product of this Markovnikov addition of water would just be this, where we have our methyl group here, and then we would have this hydroxyl. Of course, we're going to end up with a pair of enantiomers. So we'll put here, we'll just write racemic. Okay, that is what we would get from oxymercuration-demercuration. If we had done an acid-catalyzed reaction, meaning just using H3O+, what we would have ended up would be this. We would have our alkene. It's going to react with our acid, so H3O+. Let's draw that out. We're going to get our proton transfer like this, and let's draw the carbocation that's formed. The carbocation, oops, I left out a methyl group. The carbocation is going to be this carbocation, but that carbocation can undergo a methyl shift like this to give you a tertiary carbocation. So let's draw that. That's going to look like this. So now I've got this, my tertiary carbocation. Now, after the nucleophilic attack and proton transfer, I'm going to end up with the hydroxyl at this position as opposed to where I want it. So I end up with a tertiary alcohol instead of the secondary alcohol if I treated it with acid. Now, of course, I'd probably end up with a mixture, right? I'd end up with a racemic mixture of the blue one, and then there's no chiral centers in here, so I'd end up with this one as well. But again, you end up with a mixture. Let's try the same thing with the next one. I'm going to have to switch over to a blank document in order to do that, since we're running out of space. So this is question 8.16. So let me pencil this in. This is 8.16b. We're starting it with this alkene. So this would be what? 3,3-dimethyl 1-butene. And we're treating it with mercuric acetate in water in the first step and sodium borohydride in the second step. This is oxymercuration-demercuration. It's nothing more than the Markovnikov addition of water across the double bond, but we avoid carbocation rearrangements. If I was to take that same alkene and I treated it with aqueous acid, so I'm just going to put H+, I would end up with this secondary carbocation, which can undergo a methyl shift to produce this tertiary carbocation. And so now I could have the secondary carbocation undergoing nucleophilic attack by water, followed by a proton transfer, and I could have it here for the black one. So I'm going to end up with two products. I'm going to end up with this compound, which would be racemic, because I have a stereocenter here. So this would be racemic. And then I'm also going to end up with this compound, which is achiral. And so I end up with a mixture in this case. So oxymercuration is very useful. Now, one thing that I will caution you on is if I give you a question on a quiz where you have a carbocation that won't rearrange and you want to add water in a Markovnikov fashion, I would use a catalytic amount of acid and water. The only time I would use oxymercuration-demercuration is if you're in a situation where the carbocation can rearrange. Why would that be? Well, a few reasons. But I'd say the major reason is that we want to avoid using mercury at all costs. Why? Because mercury is toxic. And if we can do any reactions and avoid using toxic chemicals, we will. So again, I repeat, if you can add water in a Markovnikov fashion just using catalytic amount of acid and water, no carbocation rearrangements, that would be preferred. The only time you will use Oxymercuration-Demercuration is when you have a carbocation that can undergo rearrangement.